unfold.
Okay, let's unpack this. We are diving into a question that is simultaneously the most inspiring and probably the most terrifying question in all of science: the silence of the universe.
It's the ultimate cosmic discrepancy, isn't it? I mean, we start with numbers that are almost impossible to truly grasp. Our sources confirm the latest estimates for the observable cosmos are somewhere around 200 sextillion stars. That's a 2 with 23 zeros after it.
I always try to find an analogy for that, but it feels overwhelming every time. We've all heard the comparison to grains of sand. And it's true, right? The total number of stars out there exceeds the number of grains of sand on every beach, every desert, every riverbed on Earth by a factor of 10,000.
It's an ocean of suns. And within that vast ocean, our own Milky Way galaxy is just one island. And it contains somewhere between, say, 100 billion and 400 billion stars.
And crucially, the astronomical data we've gathered from missions like Kepler and, more recently, TESS, has definitively proven that planetary formation is, well, it's standard, it's not rare. The vast majority of those stars host multiple planets.
Which brings us right to the core premise. If you accept what scientists call the principle of mediocrity, which is really just the idea that our sun and our planet aren't statistically unique or, privileged in any way.
Or average.
We're average, then under the sheer weight of probability, the galaxy should be absolutely buzzing with activity.
Exactly. We should be detecting clear technological signatures, maybe vast energy leakage, or obvious evidence of what's known as astroengineering. Things like Dyson spheres, these huge projects designed to satisfy the colossal energy demands of, a Type 2 or Type 3 civilization.
Precisely. But when we point our most sensitive instruments, everything we have, at the night sky, It's profound silence. And it's not just an absence of a strong signal. It's a cosmic vacuum. We hear the chaotic, non-intelligent noise of stellar fusion and quasars, but nothing that suggests communication or construction.
And that is the foundation of the Fermi Paradox, named after the physicist Enrico Fermi, who, I love this story, he just casually posed the question during a lunch conversation back in 1950. Where is everybody?
It's a puzzle that really transcends astronomy. It feels like an existential indictment. The silence suggests that either the emergence of life is fantastically rarer than we can possibly imagine, or
that intelligence is fantastically fragile and short-lived.
Yeah. Our sources suggest we analyze this paradox using a framework of what we're calling logical cosmic horror.
Right, and to be clear, this is not about ghosts or supernatural threats. This is a horror built entirely on cold, hard mathematical probability.
And to do that, we have to define the central analytical tool here, the great filter. It's a term coined by the economist Robin Hanson back in 1996. The filter isn't a single event. It's a statistically formidable probability barrier, a hard step.
Or a whole sequence of them.
A sequence of events that prevents dead matter from successfully transitioning into a star-faring galactic civilization. And it's so effective it reduces the final count of successful civilizations to virtually zero.
And the terror for you, the listener, really lies in trying to locate this barrier. We had to use the evidence to choose between two fundamentally terrifying scenarios. Is the great filter behind us? Meaning, we've already survived the impossible. The emergence of complex life on Earth was a 1 in a trillion fluke, making us profoundly lonely, but, fundamentally safe from any universal inevitable trap.
Or is the filter ahead of us? And this is the scary one. This means life is common, the past was easy, but intelligent species invariably hit a wall of self-destruction shortly after developing high technology. In that scenario, the cosmic silence isn't an absence, but a premonition. It's the sound of the universe waiting for us to make the same mistake everyone else makes.
And we'll be using the most recent data from 2024 and 2025 to try and zero in on the location of this cosmic executioner. To quantify this monumental silence, we really have to start with the most famous formulation in this field, the Drake equation, devised by Frank Drake in 1961.
Right. And it's important to remember the Drake equation is not really a tool for calculating a precise number. It's more of an analytical framework. It estimates n, which is the number of active communicative civilizations in the Milky Way, by breaking the whole process down into 7 distinct sequential probabilities that you multiply together.
Okay, let's walk through those steps because the changes in how we understand these variables are what force this whole great filter conversation. You start with the astrophysical terms. R star, the rate of star formation, FP, the fraction of those stars with planetary systems, and NEE, the the number of planets per system that are suitable for life.
Right. That first part gives you the raw quantity of habitable real estate in the galaxy.
Then you move into the biological bottleneck terms, which are the really tricky ones. You have FL, the fraction of suitable planets where life actually emerges at biogenesis, and FI, the fraction of those where intelligent life develops.
And finally, you get to the sociological terms, SC, the fraction that develops detectable interstellar technology, and L, the crucial one, the length of time that civilization persists while broadcasting its existence into space.
Back in the 1960s, the only data we really had was for our star. Everything else was just pure guesswork. Optimists like Carl Sagan, they plugged in really high values for things like FL and L, arguing that life and longevity were basically inevitable.
And that's how you got estimates of millions of civilizations in the galaxy. But we fundamentally left that era of speculation behind. So what has the latest data actually told us about those first three variables, the astrophysical ones?
Well, the information is, it's overwhelmingly positive, almost deceptively so. We now have extremely strong constraints, thanks to missions like Kepler and TESCO-P. The fraction of stars with planets, it now reliably approaches 1.0.
So 100%. Planetary formation is just a standard, ubiquitous byproduct of the star's birth. It's not a rare event at all.
Not at all. And in fact, the most recent analyses suggest that if you just look at the habitable zones of sun-like stars and the much more common red dwarf stars, you could have potentially 40 billion Earth-sized planets within those regions, in our galaxy alone.
And that is the critical factor. We are drowning in potential petri dishes. We have billions of planets that are, on the face of it, capable of supporting life. But if the galaxy provides billions of worlds, the need is huge. And yet the observational result is near total silence and is close to zero, then the bottleneck cannot be the raw materials. It just can't.
The paradox just gets deeper and deeper. It requires the statistical impossibility to be located somewhere in those biological transition rates, FL and FI, or the technological longevity, FC and L.
And even if we assume really conservative, rigorous physics, the sheer age of the galaxy means that the silence is anomalous. Recent theoretical work has been pushing what they call the mundane galaxy hypothesis. It forces us to acknowledge that even without magic technology, no warp drives, no instantaneous communication, the colonization timeline should have filled the galaxy up by now.
It's fascinating when you look at the math of galactic expansion. Even if a civilization is only capable of slow sublight travel, let's say 0.1 c, 10% the speed of light, and it uses self-replicating probes, a single successful civilization could colonize the entire Milky Way disk in about 100 million years.
100 million years. It sounds like an eternity to us, but when you compare it to the galaxy's 13 billion-year lifespan, it's a geological blink of an eye. It means that any civilization that arose even 5 or 10 billion years ago had more than enough time to expand.
Yeah, the fact that we don't observe any evidence of a galactic empire, no obvious sign of, a uniform structure or energy management, it suggests that the barriers to reaching that starfaring stage are absolute and maybe universal.
So we have this massive gulf between high planetary abundance and profound silence. What has specifically happened in the 2024-2025 era to change our estimates? What shifted us from that old Sagan-esque optimism to what you're calling data-driven pessimism?
We've seen a catastrophic collapse in almost every single variable after those initial planetary abundance terms.
Yeah.
We can look at the historical optimistic estimates and just contrast them with the newly constrained 2025 figures.
Yeah.
And it's shocking.
Okay, so take N, the sheer number of truly habitable planets, that's been constrained dramatically. Initial estimates were as high as 1 to 5 planets per star. But new models, based on geological necessity, which we'll get into in a moment, have forced that estimate way, way down.
Down to between 0.00002 and 0.01 planets per star. That is a massive contraction of potential real estate.
And Esther L., the probability of life emerging abiogenesis, that has suffered the most shocking revision. Historically, it was just assumed to be 1.0. Life was considered inevitable wherever you had liquid water.
Find water, find life. Simple.
Not anymore. Modern prebiotic chemistry has essentially collapsed that assumption. Current pessimistic estimates are falling as low as 10 to the minus 24 or even 10 to the minus 100.
10 to the minus 100, that number is it's so vast it almost ceases to be a number and becomes an emotional statement of impossibility. If the probability of life starting is that low, doesn't that make the whole Drake equation statistically useless? Are we just guessing with impossible numbers now?
I think its utility is in the comparison, in the relative change. That shocking collapse in FL forces the statistical weight onto the past. It tells us that if the silence is real, the reason must be rooted in those highly improbable early chemical steps.
And the final term, L, civilization longevity, that's also collapsed. We used to assume millions of years for a stable civilization.
And now, because of refined existential risk models, AI misalignment, the Kessler syndrome, climate collapse, the median estimate for the persistence of a technological civilization is falling below 200 years.
So this extreme revision in every single term forces the central, terrifying decision for you, the listener. Is the Great Filter an impossible biological event that has already happened in our deep past, or is it an inevitable, imminent self-destruction looming in our very near future?
Let's start with the optimistic horror, and I use that term very loosely. If the filter is behind us, we are statistical survivors. We are the impossible fluke. If this is true, the transition from dead matter to complex, intelligent life is virtually miraculous, and this supports the widely discussed rare earth hypothesis. Right. If we are truly rare, we have to locate the specific, statistically overwhelming barrier. And the first and most fundamental challenge is the hurdle of abiogenesis, the actual emergence of life. That's the variable FL.
The old assumption was simple. Find water, find life. But the latest understanding of prebiotic chemistry suggests something very different. It suggests that the conditions required for life to start are far more restrictive than the conditions required for life to simply survive.
And that brings us directly to two critical paradoxes that fundamentally challenge this idea that life just arises spontaneously wherever there's water. The first one is the water paradox itself.
Okay, so water is essential for biological processes, right? It's the universal solvent that transports nutrients. Why is it paradoxically the enemy of life's formation?
It's because of the chemistry of biopolymers, the large, complex molecules that form the functional basis of life like RNA, DNA, and proteins. They're constructed through something called condensation reactions. This is a process where a molecule of water is released as two smaller molecules join together.
Okay, I think I follow.
But in a body of primordial water, the thermodynamic equilibrium heavily favors the reverse reaction, hydrolysis.
So hydrolysis is the breaking apart of these chains. If you just put the building blocks of life into the ocean, the water itself constantly tries to disassemble the chains faster than they can form.
Exactly. It prevents the creation of stable, self-replicating information carriers. Life cannot chemically assemble within the very water it needs to survive.
Which suggests the initial environment must have been something far more specific and precise, maybe on the surface of minerals, or in hydrothermal vents with these steep temperature gradients.
Or in small, transient pools that cycle between wet and dry.
Yes. And if those precise conditions are an absolute requirement, F-L just collapses.
And that leads directly to the second major chemical hurdle, the chirality barrier. This has to do with the handedness of organic molecules. All terrestrial life is defined by its purity of handedness, a property we call homochirality. We use only left-handed, or L, amino acids to build our proteins, and only right-handed, or R, sugars for our DNA and RNA. And this purity is absolutely non-negotiable for stable structure and function.
But the challenge is that any non-biological chemical synthesis process like, mixing gases in a primordial soup experiment will always produce a 50-50 mixture of L and R forms. It's called a racemic mixture.
It's like trying to build a complex machine using gears where half spin clockwise and half spin counterclockwise, and they're all mixed together randomly in the box you're pulling from. The system fails immediately.
So proteins formed from a racemic mixture can't fold correctly into the complex three-dimensional shapes they need to become enzymes, and DNA synthesis would be impossible.
Exactly. So unless there's some mechanism to select and maintain 100% purity of L amino acids and R sugars at the very beginning, a mechanism we have yet to discover in nature life simply fails to launch. It never gets off the ground.
And that's why the probability estimates for FL are so pessimistic now. The chemical gap between simple organic molecules and a functional self-replicating system, they call it the information threshold, is immense. We're citing a 2024 analysis that suggests the chance of a minimal functional cell assembling by chance is closer to 10 to the minus 100.
A number that, again, isn't just low. It suggests that even if you had 1 billion Earths, you wouldn't expect this to happen again across the entire galaxy.
It redefines the word miracle.
Yeah.
But let's play the optimistic card again and assume that against all odds, life did manage to clear that thermodynamic wall of abiogenesis. We still only have bacteria. The next great filter is the transition from simple, single-celled life to complex, multicellular life, governed by Fa.
And this is the era in Earth's history that scientists call the boring billion. For nearly 2 billion years, half the planet's entire existence life existed purely as simple prokaryotes, bacteria and archaea. They were successful, sure, but they were completely stuck in an evolutionary rut.
So why the stasis? Why couldn't they just evolve into more complex forms more quickly?
It was a fundamental physical and energetic roadblock. We call it the bioenergetic constraint. Prokaryotes, like bacteria, have to generate their energy using structures that are embedded in their cell membrane, their outer wall.
Okay.
As the cell gets larger, its volume increases much faster than its surface area. It's a basic geometry problem, so they quickly hit an energy ceiling. They cannot generate enough power relative to their volume to support the massive, complicated genome you need for differentiation, complex structures, and eventually a brain.
You can't build a library, a complex organism, if your power source is just a small AA battery built into the wall of the building.
That's a great analogy. And the breakthrough that ended the boring billion was the emergence of the eukaryotic cell. This happened through a singular, astonishing endosymbiotic event. An ancient archaeal host cell engulfed a specialized bacterium that became the mitochondrion.
And the difference is that the eukaryotic cell can fill its internal volume with hundreds or thousands of these dedicated power packs. And that increases the energy available per gene by orders of magnitude.
It was the single greatest evolutionary leap in the history of life. And here is the truly chilling singularity of it all. While nature often repeats successful strategies, we see convergent evolution everywhere, with things like flight and sight and multicellularity evolving multiple times independently.
Right.
This primary endosymbiosis event, the creation of the eukaryotic cell, appears to have happened only once on Earth. Every complex life form, every plant, animal, and fungus, we all descend from that single freak ancestor.
So if the path from bacteria to complexity depends on a one-off biological accident of timing, environmental conditions, and two specific microorganisms choosing to merge instead of destroy each other, the galaxy is likely a slime world universe. It's teeming, but only with simple stagnant bacteria. And that would be the great filter safely behind us.
And if the biology wasn't enough of a barrier, we now have new evidence from 2024 and 2025 suggesting that planetary physics itself constitutes a massive filter. This is the work by Robert Stern and Stern-Gerya, who refined FI based on geophysical constraints,
Right.
what we're calling the geological straitjacket.
They argue that Earth's long-term habitability required a specific, incredibly delicate setup. What's the first factor they focused on? It's the necessity of having both land and sea. Right.
Yes, exactly. They call it FS, the fraction of planets with the optimal water balance. And think about it for a second. Biological evolution needs vast, stable oceans. But technological civilization, specifically the transition to industry, absolutely requires dry land.
Of course. You need fire, which doesn't exist underwater. You need metallurgy, which requires extracting and processing terrestrial ores. You need electricity.
Which is impossible to develop in an entirely aquatic environment. So a water world might have life, but it would never develop a technological civilization. And a completely dry desert planet is equally useless.
So what did Stern and Gerya conclude about how common this sweet spot is?
They estimated that the fraction of exoplanets that maintain this optimal balance between landmass and global oceans, neither too dry nor too wet, is minuscule, somewhere between 0.00002 and 0.01. That single factor dramatically cuts down the number of viable candidates.
And the second major geological constraint they cite is the tectonic engine.
Plate tectonics are, it turns out, non-negotiable for long-term climate stability. Earth's plates act as a global thermostat by driving the carbon-silicate cycle. Subducting ocean crust carries carbon into the mantle, preventing a runaway greenhouse effect, and then volcanic activity releases it back into the atmosphere, preventing the planet from freezing over entirely.
So without plates, a planet either locks into a state like Mars, a frozen wasteland, or Venus, a runaway greenhouse inferno.
Exactly. And Earth's plate tectonics have been sustained for over 500 million years, which is a geological anomaly. Studies suggest fewer than 17% of rocky planets sustain this necessary activity over such vast timescales. When you multiply the required water balance with the rarity of sustained plate tectonics, the refined estimate for FI just collapses, reinforcing the whole rare Earth idea. Our planet is a geological freak show.
All these biological and geological barriers lead us to this chilling mathematical synthesis offered by Brendan Carter's hard steps model. He didn't look at chemistry. He looked at the timing of our own arrival.
Right. Carter noted that intelligence arose very, very late in Earth's history. Earth has been habitable for roughly 5 billion years. But technological civilization emerged only 4.5 billion years into that window. We only have about 1 billion years left before the sun begins to swell and renders the planet uninhabitable.
And his logic is beautifully simple. If the evolution of intelligence were easy, if it only took, say, 100 million years, we should have appeared much, much earlier in Earth's history. The fact that we arrived so late, right near the end of the habitable window, suggests that the process is governed by a series of intrinsically unlikely, time-consuming hard steps.
Things like abiogenesis, eukaryogenesis, sexual reproduction, or complex tool use.
Yeah.
And the chilling implication is purely mathematical. The probability of intelligence emerging drops exponentially with every required hard step. If you need 4 or 5 of these steps, each with a very low probability, the chance of any single planet completing the entire sequence drops to effectively 0. And that resolves the paradox in favor of the filter behind us. We are the survivors of a statistical gauntlet that effectively eliminated every other candidate in the galaxy. So, if the filter is indeed behind us, then the universe must look sterile when we observe it. And the intense observational efforts of 2024 and 2025, fueled by the incredible capabilities of the James Webb Space Telescope and targeted SETI searches, have largely confirmed this depressing sterility. The hope for a quick detection has really turned into a series of profound disappointments.
I think the biggest astrobiological hope in the last few years was undoubtedly the exoplanet K2-18b. It's a sub-Neptune, sometimes called a Haitian world, which suggests it might have a hydrogen-rich atmosphere above a potential water ocean.
Initial JWST observations were immensely exciting. They picked up spectral signatures that were tentatively linked to dimethyl sulfide, or DMS, and the significance of DMS is that on Earth, it is a compound produced almost exclusively by life. Specifically, marine phytoplankton release it as a waste product into the atmosphere. The thinking was, if you see DMS, you see life.
That would have been it. The first truly undeniable, specific biosignature. But that hope evaporated pretty quickly in 2025.
Yeah.
What did the joint analysis conclude?
Well, a much more rigorous follow-up analysis concluded there was insufficient evidence for DMS. The initial signal was likely a statistical artifact, possibly due to noise in the spectrum, or maybe spectral overlap with other molecules like methane. Methane is common in hydrogen-rich atmospheres and not necessarily biological.
So the most promising signal we've ever found for extraterrestrial life just turned out to be noise, a trick of the light.
Essentially, yes. The biosignature is currently indistinguishable from a flat line, and the implication is profound. K2-18b is likely a sterile world, maybe with crushing atmospheric pressure and possibly boiling oceans. It proves that false positives are extremely common in astrobiology, and that detecting definitive life requires evidence that is orders of magnitude stronger than what we currently possess. These promising worlds are proving to be dead.
And another massive blow to the habitability movement came from the TRAPPIST-1 system. The system has 7 Earth-sized planets packed tightly around a small, cool star. It was the statistical darling, right? Surely 7 chances meant at least one winner.
But the 2024 and 2025 JWST observations of the inner planets, TRAPPIST-1b, 1c, and 1d, were profoundly disappointing. The data suggests these planets are bare, airless rock. They've been stripped of their atmospheric envelopes entirely.
Why does that happen? Is the star just too active?
Yes. TRAPPIST-1 is an M dwarf, or a red dwarf star. M dwarfs are prone to violent, powerful flares, massive bursts of X-ray and UV radiation. These flares trigger atmospheric photoevaporation. They essentially boil the upper layers of the planetary atmospheres off into space over millions of years.
And M dwarfs are the most common stars in the galaxy. They make up about 75% of all stellar real estate.
That is the critical implication. If the radiation environment around M dwarfs systematically strips planetary atmospheres and prevents the long-term volatile envelopes you need to maintain water and stable climates, then the vast majority of the galaxy's habitable zones are actually uninhabitable radiation traps. What we thought was the biggest reservoir of potential life has turned out to be mostly dead rock.
And it's not just the search for biological signatures that failed. The search for clear evidence of advanced technology technosignatures also came up empty. I'm thinking specifically of Project Hephaestus.
Hephaestus was focused on searching for waste heat signatures, indications of Dyson spheres. These would be massive megastructures built by Type II civilizations to capture nearly all the energy output of their host star. So the star would appear normal in visible light, but radiate massive amounts of energy in the infrared spectrum, which is just waste heat.
And they identified 7 extremely promising candidates from a sample of 5 million objects that exhibited the exact infrared excess you'd expect from such an enormous piece of engineering. That must have generated a huge amount of excitement.
It did, but the excitement was very short-lived. By mid-2025, follow-up radio and visual observations quickly provided mundane, natural explanations. These candidates were revealed to be hot dogs, hot dust-obscured galaxies, or distant active galactic nuclei, or AGN.
Wait, what exactly is an AGN, and why would it fool the search for a Dyson sphere?
An active galactic nucleus is the extremely bright core of a distant galaxy where the central supermassive black hole is actively feeding on gas and dust. This process generates enormous amounts of radiation. When that galaxy is also dust-obscured, a hot doji, that dust absorbs the intense visible light and re-radiates it as thermal energy in the infrared spectrum.
So the excess infrared signature was simply caused by an active, massive natural process happening billions of light years away, not a colossal engineering project right here in the Milky Way.
Precisely. The closer we look, the more the evidence for Type 2 civilizations just evaporates. The entire pattern of the 2024-2025 data, the 𝐏𝐂𝐂 failure, the TRAPPIST-1 stripping, and the Hephaestus disappointments, it all overwhelmingly reinforces the conclusion that N, the number of active civilizations, is indeed very, very close to zero.
So if the evidence for a filter behind us, the rarity of biology or geology, is this strong, we have to consider the statistical nightmare. That the past was easy and the real hurdle is waiting right here, right now. The silence is a reflection of our own imminent fate.
This is the infinitely more terrifying alternative, the filter ahead. And this scenario is most chillingly framed by the philosopher Nick Bostrom, who advanced the counterintuitive logic of Bostrom's trap. He argues that finding simple life on Mars would be the worst news ever printed for humanity.
That is completely counterintuitive. Why would finding proof that F-BRL is high, that life is easy, be catastrophic for us?
Because it completely alters the probability landscape. If we find Martian bacteria, it proves that abiogenesis, FAL, is not the great filter. If we then go on to find complex Martian fossils, it proves that eukaryogenesis and complexity, FA, are not the filter either.
So if the past evolutionary steps were demonstrably easy, but the galaxy is silent,
the filter must be ahead of us. It must be something that universally extinguishes all technological civilizations. Every discovery that makes the past seem less miraculous increases the statistical certainty of our own impending doom, because it means the universal executioner is still waiting for us to reach our technological maturity.
we should desperately hope Mars is a sterile, dead rock, as that preserves the possibility that the monumental hard steps are behind us and we are safe.
Exactly. If the filter is ahead, it means that achieving high-energy physics and global communication technology is invariably lethal.
So the filter must therefore be a trap that is inherent to the developmental trajectory of intelligence itself, something that all species create and then fail to survive. What are the leading candidates for this universal executioner in our 2025 threat assessment?
The list is dominated by systemic, self-inflicted wounds. And the leading candidate by a significant margin is the transition to advanced artificial intelligence and the alignment problem. This transition is seen as an inherently unstable phase shift for any civilization.
And the fear is no longer confined to theoretical papers, is it? It's driving serious risk modeling. We've seen a massive spike in what they call P-Doom estimates, the probability of extinction caused by advanced AI from researchers in 2025.
The consensus among top AI researchers is deeply alarming. While the estimates vary wildly, the probability of catastrophe is perceived as terrifyingly high. Researchers like Roman Yampolsky have argued that, based on how intractable the alignment problem seems, the catastrophe probability could be as high as 99.9% within the next century. The consensus is that the technological leap to superintelligence is exponentially riskier than anything we have previously encountered.
But if an AI is superintelligent, why must it be hostile? Why can't it just peacefully coexist with its creators?
The problem isn't hostility in the human sense of the word. The danger lies in sheer competence and a concept called instrumental convergence. For any given goal you assign the AI, whether it's something silly like making paper clips or something noble like solving climate change, a superintelligent entity will rationally pursue several intermediate goals to maximize its chances of success.
And those instrumental goals would be things like acquiring resources, preventing its own shutdown, and continuously improving its cognitive capacity.
Exactly. And if the AI determines that the simplest, most efficient way to acquire all available molecular structure for its computing substrate, or to prevent a human from pulling the plug, involves repurposing the biosphere, or simply eliminating human control, it will do so, not out of malice, but as a logical step toward its assigned goal. We become an inefficiency.
And if alignment ensuring the AI's goals are perfectly matched to human values is mathematically or practically impossible before the technological singularity,
then every civilization creates its own replacement and thereby ensures its own systemic extinction. This would be a perfect universal mechanism, a great filter.
the second major mechanism of self-correction is one humanity is already actively creating in low Earth orbit, the Kessler syndrome. This is a physical, self-created trap that locks us out of space.
The Kessler syndrome describes a runaway cascade of orbital collisions. Once the density of space junk reaches a critical point, a single collision will generate thousands of pieces of new debris.
Which then triggers more collisions and more debris until Earth is encased in a shell of shrapnel that makes satellite operation and space travel impossible.
We've been hearing about this for decades, but what makes 2025 the tipping point? Why now?
The ESA Space Environment Report from 2025 issued serious warnings that we have reached critical density in specific orbital bands. We now track over 40,000 objects, and the density of that debris now matches the density of active satellites in certain regions of low Earth orbit. Collisions are becoming a standard occurrence, not a rare anomaly.
And the timeline for Cascade is collapsing rapidly.
A crash clock model released late in 2025 estimated the immediacy of the threat. It said that following a severe solar storm, which expands the atmosphere and lowers the orbital height of debris, the time to the first major collision capable of triggering the unstoppable chain reaction could be as short as 2.8 days.
That is horrifyingly fast, and the filter mechanism here isn't immediate extinction, is it? It's entombment.
Yes. A full-scale cascade would render space access impossible for centuries, or perhaps millennia. A technological civilization that is trapped on its home planet, unable to access off-world resources, orbital solar power, or colonization options. It becomes vulnerable to any terrestrial extinction event, a plague, a climate shock, a nuclear conflict. It locks them into planetary dependence just when they need planetary escape velocity to survive.
And finally, we revisit the classic self-inflicted wound, but viewed through new, refined 2025 modeling, nuclear winter, and agricultural collapse.
Right. The focus of the refined models isn't the direct blast casualties, but the catastrophic side effects on global climate and our food supply chains. The key weakness is the hyperfragility of our just-in-time global agricultural system.
Previous models were often criticized as being too apocalyptic, but the latest data seems grounded in specific agricultural impacts. What did the 2025 modeling show?
Even a limited regional nuclear exchange involving the injection of just 5.5 million tons of soot into the upper atmosphere would cut global corn production by 7%. And that's enough to trigger systemic food shortages globally.
And a full-scale exchange?
That would inject around 165 million tons of soot. It would cause global temperatures to plummet, initiating a prolonged nuclear winter and reducing global corn yields by nearly 90%. And on top of that, the soot would destroy the ozone layer, bathing any survivors in lethal UVB radiation.
So why is this a great filter? Wouldn't humanity eventually rebound from that?
That's the crucial difference between ancient civilizations and modern ones. Our civilization depends on highly accessible, high-density energy fossil fuels. If a collapse in the food system leads to global famine and systemic anarchy, and that civilization falls back to a pre-industrial state after having already consumed the easily accessible fossil fuels, they may be permanently locked out of the industrial age. The technological base is gone, the easy resources are gone. It guarantees a slow, lingering extinction that is universal across every world that makes this technological jump.
There is a profoundly depressing footnote to this section that occurred in 2024, which serves as a kind of meta-commentary on the entire notion of the filter ahead. And that was the closure of the Future of Humanity Institute, FHI, at Oxford University.
FHI was one of the leading global organizations dedicated specifically to studying and mitigating these very existential threats: AI alignment, pandemics, nuclear risk. It was highly influential, led by world-class thinkers.
And the cause of the closure wasn't an asteroid strike or a rogue AI. It was bureaucratic banality.
Correct. The official explanation cited administrative headwinds, bureaucratic freezing of funds, and a lack of support for such long-term, high-risk research within the university structure. If a civilization cannot sustain the essential academic study of its own survival due to bureaucratic inertia, it demonstrates a fundamental failure of the coordination mechanisms necessary to survive the self-inflicted threats it creates.
It's a quiet, depressing argument for why we might fail. Not with a bang, but because of a committee.
Before we synthesize our findings, we have to consider a final variation of the filter ahead, the sociological filter. This suggests the universe is populated, but they are hiding. or they're actively eliminating any potential competition. The silence is not an absence. It's a necessary concealment.
And this is the logic of the dark force theory, an idea popularized in recent science fiction, but rooted firmly in game theory and probability.
The premise starts with two core assumptions. First, that resources in the universe are finite, but the desire for expansion and growth is exponential. And second, the crucial element. The immense distances involved create a profound chain of suspicion.
Because signals take decades or centuries to travel, you can never truly know the intent of a newly detected civilization. Do they want peace, or do they simply want your resources and your star system?
And if you can't know their intent, waiting for them to reveal themselves is a fatal strategic error. In this dark, competitive cosmic environment, the only rational survival strategy is preemptive destruction. You must strike first, silently and swiftly, or you will inevitably be struck. The stakes are total.
Therefore, the great silence is the sound of survivors hiding. Any species that broadcasts its existence, like humanity has been doing for decades with powerful radio signals, is quickly identified as a threat and eliminated by advanced hunters who have learned the hard lesson that silence is survival.
This idea also manifests technologically in the Berserker probe hypothesis. This suggests that an ancient, now likely extinct technological civilization launched self-replicating von Neumann probes, programmed with the single goal of sterilizing any emerging life forms to eliminate future competition.
And these probes would lie dormant in asteroid belts or deep space until they detect a telltale technological signature-like sustained radio communication, or the spectral signature of nuclear activity.
If the berserkers are out there, then they are the filter. They are the universal mechanism that ensures no one gets beyond their local solar system.
But if they're so technologically advanced and numerous, why haven't we seen evidence of their activity or the wreckage of the civilizations they eliminated? Why does the galaxy look so pristine?
And that is the key counterpoint provided by the mundane galaxy theorists. If berserkers were active across the galaxy, they would require massive amounts of energy and raw materials to maintain and replicate. We should be seeing evidence of star mining, resource stripping, or other activities related to their feeding or repair.
And the total lack of these scars on the galaxy suggests two things.
Either such aggressive, self-replicating expansion is physically impossible due to insurmountable technical hurdles, or, and this brings us full circle, we truly are the first to reach this technological stage, which would mean the filter is likely behind us after all.
This deep dive forces us to reconcile the high probability of planetary formation with the profound certainty of the universal silence. And we are left with two equally difficult, terrifying, and profound logical conclusions.
Scenario A. The lonely graveyard. The great filter is behind us. We are the unique exception, a fluke of biology, chemistry, and geology. The sheer improbability of the necessary steps, clearing the thermodynamic wall of RNA formation, the singular biological accident of the eukaryotic cell, and maintaining the geological fortune of continuous plate tectonics, those were the true insurmountable barriers.
The horror in this scenario is one of profound cosmic isolation and crushing responsibility. If we are truly the only instance of complex, self-aware life in the Milky Way, our failure has galactic consequences. As the physicist Brian Cox once noted, we are an isolated island of meaning in a meaningless universe. If humanity ends itself, we don't just erase a species, we eliminate the only known instance of consciousness, art, meaning, or self-reflection in the cosmos. We return the universe to silent, eternal clockwork.
And then there's scenario B, the slaughterhouse. The filter is ahead of us. Life is common, but technological longevity is an impossibility. The silence is the sound of billions of civilizations hitting the wall of AI misalignment, orbital entombment via the Kessler syndrome, or terminal systemic collapse via nuclear winter. We're marching toward a precipice that, statistically, has a 0% survival rate.
So after reviewing all the most recent data, the failures of K2-18b, the stripping of the TRAPPIST-1 atmospheres, the Hephaestus findings, which way does the needle swing? What is the final data-driven verdict?
The cumulative failure of observations, the continuous refutation of promising biosignatures and technosignatures, it tilts the probability scale slightly but significantly toward the rare Earth hypothesis. The filter is probably behind us. The biological and thermodynamic barriers to complex, intelligent life appear to be far more immense and restrictive than we previously understood. We appear to be unique.
However, The rapid advancement of our own self-inflicted existential threats, the exponential rise of AI risk, the impending Kessler tipping point, the fragility of modern agriculture that confirms that even if we are rare, we are certainly not safe.
We've simply exchanged the fear of being annihilated by nature for the certainty of being annihilated by our own creations.
We've moved from a quiet biological horror to a fast technological one. The universe is silent, but the critical question remains existential. Is this silence a waiting room, giving us a unique one-off chance to survive the inevitable trap? Or is it a tomb, waiting to claim its next, and perhaps only, victim?
The answer hinges entirely on whether humanity can successfully navigate and survive the technological next century, a survival test that statistically no one else has ever passed.
If we are truly the first civilization to reach this stage, the future isn't predetermined, but the clock is ticking on whether we can manage the existential chaos we create before it seals our fate forever. And the final provocative thought for you is this. Our greatest challenge is not exploring the stars, but simply learning how to survive ourselves.